All right, welcome everyone to Jonathan Hayes' presentation of implementing the graph operation with GraphDefinitions.
All right, great, thank you, Dave. And thank you everybody for coming on this final day of FHIR DevDays. So as was mentioned, we're gonna be talking about the graph operation and how we used it to solve some pretty complex data requirements in our own product. So really quickly, my name is Jonathan Hayes, as was mentioned. I'm a technical lead at Verily Life Sciences. If you don't know, Verily was previously Google Life Sciences and then broke off into its own company. And I'm specifically part of the Precision Health platform. So this is kind of like the data backbone to a lot of the products that we offer in the care and research spaces. So probably good to start with what is the graph operation in case you're not familiar. So essentially what this is an operation which returns a graph of FHIR resources based on a graph definition. And you're probably thinking that's not very helpful because I also don't know what a graph definition is. So we'll get to that momentarily. Just for a quick reference, the server URL here. So we have your FHIR server URL, the resource type, the resource ID, and the graph endpoint. And the important thing here is it's invoked on a single resource with the graph definition informing the server what the other resources should be included in the result bundle based on the data relationships that you want to define. So I'll jump out of the slides real quick just to go to the spec here. So this is the graph definition resource, as I mentioned. So I'll call out a couple of things here. Can you see the cursor? Yes, perfect. So importantly, the name and status are required. Pretty standard. You want to make sure it's active if you're actually going to be using it for the status. But the important part here is the start, which is a code. So this is the resource type that you want to start your graph on. This is like the root node of your graph. So you say you want to start on a patient and then build it from there. And then you have this nested link field. So you can see within link, you can have more links. So this is recursive and nested. And in each link target, you have a type. Again, this is a resource type that you want to connect to. And parameters. So this is going to essentially be how you craft a FHIR search to connect the data model there. And we will go into examples further on, but for now, at least that gives you a bit of an idea of what this graph definition is going to look like. There we go. So our specific use case was a real-time plugin architecture. Essentially what we're doing is we're processing a FHIR resource that was either just created or modified in our FHIR store, and we're getting a notification through technology like PubSub. So what we need to do is we need to gather all of the relevant data that's related to the resource for each plugin that wants to process the resource. So we have a central orchestrator and a bunch of plugins that plug into that and tell us what they want to process and what they need to be able to process. So the problem is how do we handle a plugin that says, when you get a patient that comes in, I want to process that patient, but to do that, I need their contact information and all of that contact information's encounters. So maybe you're processing something like a family medical history. You want to check for a history of heart disease in their connections. So we need to have multiple layers of connected resources here, and obviously this is not something you can hard code or define ahead of time. This is dynamic because we're in a real-time system. Something is coming in that we don't know its ID until it happens. So this is kind of the problem that we're dealing with. So yeah, succinctly said, in other words, we need to be able to execute FHIR searches for an arbitrarily deep and complex graph of related resources. Thankfully, that is exactly what the graph operation is meant to do and what those graph definition resources capture the details of. And to quote the spec, we want to define a graph of resources that we're going to return in a query. There is a single problem though, and it's a big one. The problem is that this graph operation is not implemented by hyperscalars. And frankly, it's for a good reason. There are a lot of really big challenges for implementing this at a global scale where you're giving a lot of control to the clients calling your FHIR server. There's a risk of infinite recursion or graph depth in the request. So if somebody hits your FHIR server with a graph that's poorly defined that has a cycle in it, you're gonna run into big problems. The graph that they send you could be expensive or it could have unoptimized queries that eat up bandwidth. So maybe the first search they do at the root node is grabbing 1,000 patients, and then now you're doing recursively a arbitrary number of recursive searches on 1,000 patients. So you're going to eat up network bandwidth, CPU time, memory, all that stuff. And again, large resources can be part of those graphs, so that can cause a really high variance in the API performance and the request latency that you're returning. So if you have an SLO to have hit a certain latency for 95% of your requests, you're going to have a problem when you're allowing people to send you things that could be returning huge resources. So our approach was to essentially leverage graph definitions for our specific use cases. So we created predefined graph definitions to map out all the data relationships for all of our use cases. And then what we did, since the FHIR server doesn't have this graph implemented, in our own FHIR client's interface, we added the graph function and implemented it under the hood. So all of the individual pieces of business logic that are calling our FHIR client, they're none the wiser. They just think there's a graph implementation. And under the hood, instead of calling out to a FHIR server like Google Cloud Healthcare or AWS Fireworks, we are actually doing this under the hood. So what's happening under the hood is our FHIR client is performing a recursive breadth first search of the graph. And so each node in the graph is essentially, again, it has a target and it has a FHIR search that you're performing. And the results of that individual FHIR search then become the inputs to the next children nodes in that graph. And what you get at the end of this entire operation, you have a single bundle of FHIR resources. So what we're doing here is we're defining the graph definitions on the client side by predefining these graph definitions ahead of time, and that allows us to control for those, all those bad edge cases we just talked about. And also by predefining those relationships, we isolate the responsibility of generically processing the graph with the actual FHIR server interactions. So when we're talking to the FHIR server, it's just a bunch of regular searches. It's none the wiser. The clients that are calling our internal interface are also none the wiser, but under the hood, we've handled that responsibility in that one area. And again, this also solves our infinite recursion problem because we're going ahead and defining these use cases ahead of time, and we're reviewing them to make sure they don't have any of these bad edge cases. So now we'll get to the actual example. So let's say we are given an encounter resource, and in that encounter is representing a situation where a patient received a diagnosis. So what we want to do is we want to fetch the practitioner that made that diagnosis. So not only do we need to find the patient, but we also need to find the practitioner for that as well. So the data model here is we have a condition with an encounter field that references the encounter. So that's how we can connect the condition and the encounter. And then the condition also has an asserter field, which is a reference to a practitioner. So we have two connections here to go from encounter to condition to practitioner, and we need to be able to do both of those connections in this graph. So here's a quick example of a graph definition that would solve this problem for us. So we have, again, just simple ID, name, status we've set to active so that we can use it. But the important part here is now we're saying at the start, we want to start with that encounter resource that came in. And then the first target that we want to have, the first connection in our data model, is a condition resource. And the parameters here for this FHIR search are encounter equals type and ID. Now, you can see the type and the ID here are in braces. So in our implementation, we've actually supported type, ID, and version as kind of placeholder variables. So at every node in the graph, it knows to take that resource that you're at and autofill the type, ID, and version dynamically. So that allows us to be a lot more creative with the FHIR searches that we can use to connect these resources. So that's the first one. So this will essentially produce a FHIR search of condition where encounter is, say, encounter/123. And then we go one level deeper. Now that we've returned that condition resource, we have a target for a practitioner, which is what we eventually want. And again, we're doing another FHIR search here. You'll notice that this one actually is using FHIR paths. So we're saying condition.asserter, that's the field. And we're getting the reference and doing some funny business here to get rid of the prefix and only the ID. And then we're basically doing a FHIR search to get the practitioner where that ID is the one that we have from our condition. So now that we've gotten that figured out, how do we actually continue supercharging the performance of this implementation? We already talked about how we solved the infinite recursion problem, but we still need to solve the problem of expensive queries and large resources. And the way that we can solve that is we can introduce a proxy layer. So this proxy layer is going to go between our services and the actual FHIR server. So what this does, obviously, gives us the ability to leverage in-memory caching so that we can store the results of common graph queries and reuse them for later. So obviously, this comes with some pretty big key benefits. So additionally, in addition to the regular benefits of caching, we actually are going to have a pretty high or a much higher hit rate than usual for this scenario because we're predefining these data relationships. So we're narrowing the scope of all the possibilities of different values that could be hit. Obviously, this is also going to help eliminate or vastly reduce the latency for common requests. And large FHIR resources and extensive graphs for infrequently changing resources, things like code systems, organizations, or other definitional resources that aren't changing very often are obviously going to be cached and heavily reused. So you can imagine an example where you have a hierarchy of organizations, maybe you're supporting multi-tenancy, and you have a graph that defines the relationships of all your organizations and their child organizations. So if that's something that you're caching, obviously the organizations aren't going to be changing very often, so that's something that you'll have a very high hit rate on for caches and have very good performance on. And lastly, I'll just mention this as well. So we have I'll shout out my colleague Matt Rodisek and Vic as well from Verily, who just yesterday here at DevDays announced that we open source our Golang implementation of FHIRpath. So you saw it in the previous slide. We are using FHIRpath throughout, and we actually support FHIRpath in every single search parameter within the graph definition itself. So I just came up with another simple example here. So we have an encounter. We want to find the encounters for a patient who's the beneficiary of a task. So the beneficiary of a task is stored in a task.for field. So what we can do is we can search for all those encounters where the subject is that patient, and the way we get that patient is through FHIRpath. So we're saying task.for, which is a bunch of references, but we're saying we want to get the references that refer to the patient using FHIRpath, and then we'll use that to search for the subject. So between the proxy layer and the FHIRpath implementation, this gives us a lot of tools to be able to craft FHIR searches that will solve a lot of different use cases, and the advanced FHIR search features as well that come with again Cloud Healthcare or Fireworks or Azure solution as well. All those things like include, rev include, and whatnot. Since those are built-in FHIR search features, you get them for free because essentially we're just crafting FHIR searches at every node in the graph. And I think that is everything. Yeah. So if you want to reach out and chat more about it, feel free to contact me at my email here at Verily and LinkedIn as well. But other than that, we have time for questions.
Thank you. Does this maybe work for identifier references?
Sorry, can you repeat that?
Does this work for identifier references?
Yeah. So identifier is something that you can search up in FHIR search. So any field that is supported in FHIR search, you can use that as your connection.
Thanks, that was interesting. Just with regard to the proxy server, how do you deal with like cache invalidation and sort of stale responses, that kind of thing?
Yeah, that's a good question. So I will preface this by saying this is something that we've started implementing and we haven't finished implementing yet. So we haven't actually finished solving that issue. I think one important thing is that there are kind of two different use cases here. Like the proxy is not going to be super great for use cases that involve things that are changing frequently, like patients or encounters or whatnot. But those definitional resources that don't change infrequently, we can probably get away with a much longer refresh time, pulling the FHIR server and checking if the versions have changed or things like that. So that's probably where the real savings are for performance.
I think I heard you mention FHIR subscription, right? Have you ever tried to use this as a core engine to support the FHIR subscription?
Sorry, can you repeat that?
The FHIR subscription, because I think this can make a very good core engine. Because in a very complicated use cases, you might have sort of like a batch update for example, in the hospital, they change the business address, right, for all the doctors. And then you get a FHIR subscription, say, okay, I'm the subscriber looking for, anything update for a particular doctor, right? So then for the implementation wise, you have to traverse the, all these, document or object tree to try to fetch whatever the change over the doctor, right? Or listen to the change. Yeah, so that's the question. Have you ever tried to, use, apply the FHIR subscription on top of that?
We haven't tried that personally. So the way we approach batch operations is more of like using SQL to find a subset of resources and then to kind of pipe those into our real-time architecture. But one thing that we can do, you might have noticed as well that I mentioned that it returns a single bundle of operations. So one limitation there in our current implementation, because we haven't had a use case that we need to expand on it, is it's a flat bundle, right? So if you want to have a better idea, maybe if you're doing a batch operation where you have a lot of, maybe you're returning a specific resource type in multiple places and you still want to retain the structure of the graph, you could look at maybe adding extensions to the graph definition itself and storing the resources, the bundles on each link in the graph. So if you're doing a larger operation, maybe that would help you kind of handle more things at once without losing information.
In that middle layer, I assume these bundles can get probably very large. Do you handle paging the bundles in any way, trying to reconcile all these resources together and try to include the right linked resources in a single page? Or is it just kind of one big bundle?
Right now, yeah, it's one big bundle. I think that's definitely something we could implement to improve in the future because, again, yeah, the problem being all these things are stored in memory, right? So this middle layer is going to have pretty high memory requirements depending on how big the graph is that we're caching. So we haven't got there yet, but that's something we probably want to do, yeah.
I was interested, you talked about code system resources. Do you support the terminology operations in FHIR?
I am not sure on that. The FHIR experts are actually sitting right behind you, so maybe afterwards we can chat all together and figure that out, yeah.
Can you go back to the slide with the graph definition where you have FHIR path? That one right there. You mentioned that you're using substring because it's a kind of a hacky way to cut off the prefix. Is there any way you might be able to do that with like a custom function?
Yeah. So we can, again, so being the FHIR path expert, you know that we can build a custom function here. So yeah, instead of being, this is obviously like hard coded for the resource type. So we could create a custom function that just takes in or processes the resource, gets the resource type, and gets a dynamic prefix and removes that to just get the ID from the resource.
Yeah, you can.
All right, if there's no more questions, thank you, Jonathan.
Great, thank you so much, everybody.